Good morning, everyone. I'm Shraddha Gupta from Potsdam Institute for Climate Impact Research and Humboldt University, Berlin, and I'm one of the ESRs in the CAFE project. Today, I will talk about our work on spatial synchronization patterns of extreme rainfall events in the Asian summer monsoon region, in which I use a complex network-based approach to shed light on the intricate relationship between the Indian and the East Asian summer monsoon, which is the two dominant components of the Asian monsoon system. I'm supervised by Professor Jürgen Kutz and Florian Pappenberger. So first, moving on, how do we construct networks for extreme precipitation? So the spatial grid points of the spatial temporal climate data set form the nodes of our network, and where each node is associated with a corresponding time series, in this case, precipitation. And I used the daily precipitation data set from the TRIM satellite data. And for the June, July, August season, which is the main monsoon season for the Asian region. And then we get the extreme event series by taking events greater than 90th percentile of the wet days for each location. Once we have all the event series, we compute similarity between every pair of event series using this method of event synchronization, which counts the number of synchronized events between every pair of event series. And if the count of the synchronized events exceeds a given significance threshold, then we consider those two the two nodes is connected, and this gives our network. Once we have our network, the next step is really to analyze the topology of the network. We use different network measures, and the network measure I primarily use here is degree, which counts the number of connections one node has with other nodes, basically giving the importance of the node with respect to how well connected they are. So this is the framework I use, and for the Asian monsoon region, when I apply the network, the functional network framework, we see that for the periods of June, July, and August, we construct individual networks for each of them. We find that in the Indian monsoon region, there are two specific, quite some notable changes, as you see when you go from June to July. The first is, if you look in the red box, which is the Arabian Sea region, you see that there is a decrease in degree as you move from June to July, and then when in the northern and central part of India, which is the blue box, you see that there is a increase in the degree as you go from June to July and August. So the next task was really to find out where these links are. Where are these boxes connected to? And for this, we compute the partial degree, which is basically we consider only those links which are arising from these boxes, and then computed the degree based on those links. And we found that the Arabian Sea region, as you see from the figure E, is primarily connected to parts in southern China, which is basically the lower and the middle reaches of the Yangtze River Valley. And the next figure, figure F, you see that the northern and central part of India, which is the core monsoon zone, is connected to northern China, among other regions in Southeast Asia and Pacific. So we identify two dominant synchronization pathways between the Indian and the East Asian summer monsoon. First is the northern mode of the southern mode of synchronization, which connects Arabian Sea and the southwestern part of India with the parts of southern China. the Yangtze River Basin, which receives rainfall from Mayu, and the northern mode, which connects the northern and central part of India with northern China near the Yellow River Basin. Next, we identified those specific times when there is high synchronization between between the pair of regions for each mode. I mean, by that I mean to say is that when the number of events in exceeds its respective 90th percentile threshold simultaneously or within a certain temporal delay for both the regions. And in doing that, when we did a month-wise distribution of these specific days when there is high synchronization, we found that the southern mode peaks in June, while the northern mode peaks later in July. So the next task was that with these days which we identified, which we call day 0, when there is high synchronization, we computed the composite of the associated large-scale atmospheric circulation and the moisture transport patterns. We found that for the southern mode, you would see that in the upper level of the troposphere, there is this strong westerly jet with strong winds over the Yangtze region. And while in the middle and the lower troposphere, you see the onset conditions of the Indian monsoon, which is basically the cyclonic conditions over the Arabian Sea region. And there is also this convergence of winds from the moisture-bearing southwesterly winds coming from the Somalian coast and the easterly winds coming from the lower boundary of the Western Pacific subtropical high. So the synchronization between the Arabian Sea region and the Yangtze Basin is basically due to the Western Pacific subtropical high first over South India, and then it moves northward towards the Yangtze Valley after a few days. For the northern mode, you see that in the upper level of the troposphere, there is this anticyclonic, cyclonic, and anticyclonic pattern, which is very favorable for strong Indian monsoon. And then you also see this, the high over Japan and parts of North China, which is the Bonin High, which is a deep vertical structure stretching throughout the troposphere. The middle and the lower levels, there you see the Western Pacific subtropical high, which has now moved northwards and is part of the Bonin High. And what is interesting is that for both the northern and central parts of India and over North China, you see a high in the upper level of the troposphere, while there is a deepened low in the lower levels at 850 hectopascal, which leads to enhanced convection and therefore synchronized rainfall in both the regions. At the same time, you see that over Japan, it's still you still have a high in the lower levels of the troposphere, which due to which Japan experiences dry spells during this period. Next, we looked into the wave patterns in the upper level of the troposphere, and we found that for the southern mode, the wave numbers associated with this wave pattern, which is emanating from North Africa, are higher, near 7 and 11, which is higher than that for the northern mode, for which the wave number is 5, which is associated, denotes the stationary Rossby wave pattern, also known as the Silk Road teleconnection pattern. And this also explains the formation of the Bonin High, which we saw in the earlier slide. We also looked into the OLR, and we found that there is negative OLR indicating positive convection over both the pairs of regions for both modes. And then we looked into the moisture transport pattern by computing the aggregates of the vertically integrated moisture transport anomaly from day 0 to day 14. And we saw for the southern mode there is connection between, there's a moisture corridor which gets established from the Arabian Sea region to the Yangtze River Valley. While for the northern mode, there is mostly a local recycling of moisture from the respective Indian and Pacific Ocean sources. So the next question was that what is the role of the intraseasonal oscillations in this northward propagation of synchronization in the monsoon season? Because there were many previous studies, which suggested that this northward propagation of synchronization was mostly due to the role of the intraseasonal oscillation. So what we did was we classified the days when there were high synchronization occurring for each mode according to the active and inactive Madden-Julian oscillation and boreal summer intraseasonal oscillation days. And we found that approximately 40% of the days of high rainfall synchronization are inactive in BSIS or MJO. And this suggests that although the intraseasonal oscillations do play an important role in this northward propagation of the synchronization mode, but they are not the sole ingredient. Next, we classified the active days of when high synchronization is occurring according to the different phases of the MJO or the BSISO. And we found that certain phases of the lower frequency mode, the MJO or the BSISO1 with a time period of around 40 to 50 days, they favor the extreme rainfall events over the Asian monsoon region. For example, phases 1 and 2 for the MJO, it favors both the northern and the southern mode, as well as the overall extreme rainfall events in June, July, August. Whereas for the higher frequency mode, the BSISO2, with a time period of 10 to 20 days, that may support the switch between the two interaction modes. As you see, like phases 2 to 6 of the BSISO2, that tends to favor the southern mode, while from phase 6 to 1, it is more favoring the northern mode. To conclude, we have used complex network approach, and it has provided a very comprehensive picture of the synchronization between the Indian and the East Asian summer monsoon. And we have identified two modes of interaction between these two components of the Asian monsoon system. And we've shown that the southern mode of synchronization occurs earlier than the northern mode of synchronization. The southern mode is mainly associated with the convergence of the winds from the southwesterly winds coming from the Somalian coast with the winds in the lower boundary of the subtropical high. And it is mostly associated with the onset of monsoon, first over India and then over the Yangtze River Valley. The northern mode is associated with the Silk Road teleconnection. And then we finally show that there are the particular phases of the MJO and the BSISO. They are associated with enhanced rainfall synchronization between the Indian and the East Asian summer monsoon. So thank you very much for your attention. And I look forward to your questions or comments.
Thank you very much, Shraddha, for your great presentation. So we can take questions now. Emilio.
Thank you, Shraddha, for the presentation. You are using same time synchronization, simultaneous synchronization, and have you tested some delay in the to construct networks?
We used some delay when we were computing the event synchronization. We played about with the optimum delay which could be used. So the results didn't change much when we are using a delay between 3 to 7 days.
Okay.
More questions? I have a question.
Yes.
I was wondering, you mentioned the southern mode peaks in June, synchronization peaks, and the other one in July. does it have anything to do with the northward movement of the ITCC? There's a seasonal, essentially,
Yeah.
fact? Or are they independent of completely?
No, it might have something to do with the northward progression of the ITCZ, but then, I mean, North China is quite high, so I'm not really sure that whether that is actually the reason causing this northward propagation. I mean, it might be one of the causes, but not the only reason for it.
Thank you. Yes.
Thank you for the presentation.
Thank you.
The analysis is based on observation from TRIM. I was wondering whether you looked at all at reanalysis or model output to see whether the same process works there.
Yeah. We also compared the results for ERA 5 with ERA 5, but I mean, that was more for evaluation as to see like whether the same patterns are seen. I mean, there was little differences, but then more or less, I mean, both the synchronization modes were there even in ERA 5. Thanks.
Yes.
In the beginning, you mentioned a 90th percentile of the 3 months, June, July, August, only for wet days. Can you say roughly what the amount of precipitation that would be?
So I don't remember the exact amount, but it's quite high because this region receives very high rainfall in this particular region. So it should be more than I think. No, I'm not. I cannot comment, but maybe I can check and let you know. Yeah. Thanks.
Any other question? If not, we can thank Shraddha again.